Well, good evening. I'm not actually sure if I like this lighting or not, but anyway, this is just a quick video of the first part of an investigation into repairing my 8902A measurement receiver. I know what is wrong with it, and what is wrong with it is that in the front panel here there is a RF amplifier, 23 dB RF amplifier, that's utilized on range 3 of the RF power, tuned RF level measurement. And when I dropped this off the bench, I must have damaged that amplifier, because the amplifier does not give enough amplification according to the performance specs. So I optimistically sent it off to Keysight for them to go and have a look at it, because they said they could repair the amplifier's unobtainium, and they said they could actually repair it. And they did. They looked at it and they gave me a quote to repair it, and that quote was $8,000. So I thought, well, no, I'm not going to do that. What I'm going to do instead is buy another 8902A off eBay and get that to pass calibration or pass performance things. And then what I'll do is I'll open up this and have a look at U1 and see if there's a possibility that it's a simple fix and I can maybe repair the amplifier myself. So what we're going to go do now is I'm going to pop open this this panel here, take out this little shim at the top, and then there are some screws on the top here, there's some screws on the bottom, and then we'll pop this front panel off and see if we can get into U1 and take a look at it. Alright, let me go do that. Okay, so here we are. I've removed the screws from the front panel. I've removed the screws from the U1 element here. This is the RF amplifier that when I had tested it was going low, running in low, and so basically it is just connected straight into here. So I can, after having undone the screws in the corner, I can actually just slide, carefully slide this this amplifier out, and there we go. What we have here is the little unit. You can see it's the RF amplifier, part number, serial number 594. This is the 594th unit off the assembly line. Not too bad. You can see the two input-output SMA connectors, and then this is going to be, one of these is going to be power. I think it's this guy here, because if you look at the circuit diagram, this jumper down here is the, let me tilt that down a little bit so you can see it. This guy here, they say that the 15 volts is coming in on one of these capacitors here. I'm not sure where it's coming in. I think it comes in here. But we're going to get 15 volts here. So when we put this in place like this guy here is going to be the 15 volt pin that's coming in. This is for the amplifier over power. So when it's being driven too hard or detects that, it's going to raise this line here, and that's going to trigger the overpower. And you can see the little connectors on the board. Let me hold it up so it's a little bit easier to see. You can, let's see if we can zoom in and give you a nice close look at that. It's got a good lock there. You can see the little, so here you can see the little hole that the pin's going to come into, and these things are little gold-plated sockets, and that the RF amplifier U1 plugs into that, and it gets its 15 volt and it's overcharged there. Actually, behind this, if we zoom out a little bit, you'll actually see the tops of the two switches. So S1 and S2, you'll see the limiter here that limits the signal, and then you'll also see AT2, which is an additional 10 dB attenuator which can be brought in line. And these two little switches behind these covers here are little 4-pole single throw coaxial switches. In later versions of the 8902A, this switch is actually replaced by some additional electronics. So now that we've got this unit out, this is supposed to be not working, and so let's go and take a look at this and see what we see. Okay, here we are. Let's take a look at the amplifier. Now, we know from the way we looked at the amplifier originally that it goes into the front of the unit like this, or into the unit like this, and so the signal is going to come in on this connector here, and it's going to leave on this connector here. And we know this is the 15 volt pin from being able to look at the circuit board, a printed circuit board, and see where the 15 volt comes in. And so we know this is the 15 volt of the amplifier. So what the manual says, if you go and look at BD2, I think it is, which gives you all the front end checks, it says to go and set up a minus 30 dB signal, feed it into the front end amp, and then see if you get 24 dB of gain. So what I have is I have my arbitrary signal generator set up, and it's outputting minus 30 dB. So let's go and stick that in. Let's hit auto here so that we can see what it is, and you can see a nice signal. And if we look down here, you'll see about 20 millivolts of signal, which is what we would expect at minus 30 dB. So I'm getting the right output signal on this. So now I need to feed this into the amplifier. So let me grab just a couple of little adapters, and these are little BNC to SMA adapters. So let's just screw those on. And then we can put our signal coming into there. We can take the output of our signal here, and then because these amplifiers all expect to run at 50 ohm, let's go and stick a 50 ohm load in there. And so now you can see, and if I step that up, you can see that I'm getting a signal that's coming through the amplifier, but it's really not being amplified at all, and that's because we don't have any power here. So what I have is my bench lab power supply. It's actually a Rigol DP832, which I actually quite like. Dave Jones did a great examination of them and design error investigation, and I have one that after it was fixed. For my purposes, it does pretty well. So what I have it set for is 15 volts and 80 milliamps, so that just in case there's any issue. And then what I've done is, because if you look at the circuit diagram, which is in page BD 22, it's in service sheet 3 anyway. BD 22 is actually the front end check. But service sheet 3 shows this, and it actually pulls the ground off one of the SMA connectors, off the input SMA connector. And so this is the plus 15 volts. This is actually amplifier overload. So when the signal's level's too high here, you'll actually get a signal, a voltage will come out, positive voltage will come out on this and telling you that it's too high. So let me connect this onto here, and then what I've done is I've just bonded the negative to earth, because the ground on my scope here is earth, so we want everything to be at the same earth level so that we can get 15 volts onto here. And so let me turn that on, and bam, you can see that I'm getting a bunch of signal there. So if I step that down, what you can see is I'm getting about 300 millivolts, which if I stick that into Excel, is going to be about 23.5 dB. Now, if you go through the front end check, the actual math, according to the front end check, says that the amplifier should be anywhere between 23 dB and about 24.8 dB, give or take 23.1 to 24.86, right? So I'm sort of in the middle there. I'm, in the lower half, but I'm not outside of the range that the manual says is reasonable for the amplifier. So now I wonder if there's a problem with the amplifier at all. Is there some reason? Now, when I had this in the actual unit, I read low. So, what I want to do now is to check to see if what could give that problem. And if we looked at the actual way it attaches, the only thing, if I can bounce down it, tap the amplifier, and so I don't think there's actually a problem. I think dropping it off my bench, while not the best thing to do, and I highly recommend not to do it, I don't think it broke this amplifier, it broke the substrate at all. So I'm wondering if there's some other issue. So the first thing I want to do is actually start turning down the voltage on my bench meter. I'm just going to turn it down by a volt at a time, and let's watch what happens to the signal. And you can see as I decrease the voltage, that I'm feeding in the amplifier, the signal gain gets progressively less. So what I may have is a power problem. But then again, I may have a problem across the range of the amplifier as well. So in that particular case, what I should do is go and utilize my network analyzer to see how the amplifier works. So let me go get set up for that, and we'll take a quick look at the network analyzing. Okay, so now we're set up to go and actually look at this utilizing my network analyzer. And so here you can see the basic screen. I'm not going to show you the screen of the actual analyzer up here because I'd reset the camera. But effectively what I'm going to go do is I'm going to tell it that we're looking at an amplifier, we want to look at transmission. The frequency that we're going to do is from 300 kilohertz to a stop of 1300 megahertz. And then what I want to send in terms of power is that minus 30 dBm signal. So now that we have that signal, what I can do is I can just refresh the screen, and we'll see a whole bunch of noise that will be coming in on the screen because we basically have our two cables completely disconnected. So what I'm going to want to do is measure across this this device. But I need to set my reference plane, and my reference plane is going to be off these endpoints here. So for the purposes of looking to see whether or not this is a good amplifier, what I'm going to do is just drop in these two guys into here, and then I'm going to take a little connector, and the little connector that we have, and you can see the connector here, and I'm just going to screw that into here and then screw it into this guy here, and then we get a good connection in there. So now what I can do is I can come up to my network analyzer. I can set the reference level at minus 24 dB, and what did I set the power for? The power is minus 30. So let me set my reference level to to 0, and if I refresh this, what we'll see is you'll see basically the effect of the cables and the connectors across that, level. And so what I'm putting in terms of power is actually minus 30 dBm, and you can see what's going on here. So what I want to do is calibrate that. So when we click normalize, what I should now see is a nice flat line across this screen. So while we do that, let me remove this through, and there you can see that we've got the nice flat line. We've been taken these items. Now there will be minimal amount of difference because of that that little through that's there, but basically we should be getting we should be pretty much getting the very little loss on that. And that's really what I'm concerned about, is like, what is the loss? Because that was what I was failing in the actual test. So let me now just go in and attach these, and remember we're at minus 30 dBm. So what I should see when I turn the power on, and let's go turn the power on now, is I should see 23.5. Remember what we saw on the oscilloscope, about 23.5 dB of gain. So let me go in and reset the reference level now to 23 dB, and if I refresh the screen, what you'll see is a pretty flat line across that reference level there. And let me take my marker now and actually move it to 11 megahertz and refresh the screen again. Now what we're going to measure is the actual gain of the amplifier right at that 11 megahertz signal level. And so if we look at this, you'll see that I'm on 11 megahertz, I'm putting out about 23.7 dB, which is well in the range, in the middle of the range for this amplifier. So you can see that it's essentially flat. Now I think what's happening at the end here, at the about, if I take my marker and run it up towards there, you're starting to look at about a gigahertz. So now you're starting to get some impact, I think, from the cables and from these cheap little SMA connectors. But you can see fundamentally it's a nice flat line across that that whole spectrum, and it's reasonable value. So I should be able to pass this test. So now I think there might be some other issue, and so let's go back now and let me turn down the voltage a bit. So let me set my marker to 11 megahertz, and now refresh this. So if you notice, I've turned the nominal 15 volts, I've turned the 15 volt supply that I should be getting down to 9 volts. And you'll notice that I've dropped about 1.5, almost 2 dB on the amplifier. Actually the amplifier stays roughly the same. So I think based on the the testing that we did with the oscilloscope and with this with my network analyzer, that we actually have a problem with the board that this goes into. And I think that the issue may really be the power connector that this is connected to. So what I want to go do is go give that a little crimp to sort of push it down a bit, and then go in and reflow the solder around it to make sure that when I dropped it I didn't break the solder, and then we'll put the unit back together again and we'll measure and see what we get out of the amplifier. Okay, let's set up for that shot and take a look at that. Okay, so these are the two items that I'm just going to try and reflow just around on this side. So let me actually just well, no, I don't want to get any flux in on there, because I don't want to get flux in on the middle of those things and maybe not you know, maybe, you know, get flux on the inside and have the pins you know, get dirty. So let me just and as a clear thing that I need to do, they're going to fall out, so I need to grab something that I can use to hold them in without actually burning my finger. So let me see if what I can do here is just press on my little heat pad. Let's go and melt this again. There we go. Okay, that looks pretty good. Let's go and melt this. Yeah, and so I think pretty reasonable there. Let me just stop the video for a moment and see if I can get my magnifying glass in and see how I did on that. Okay, I think I got that all set up. Let's go and grab the amplifier. We'll just give it a little push in, and there we go, and it's snapped in nicely there. And it's at this point that I remember that I have to actually add that. So let's unsnap this guy. Let's take our little surface here, because this item is going to this is going to actually be what helps mount the unit. So now that we've done that, let's try again and just align those little pins, push that in, and that's now sitting in there nicely. So now let's grab the four little screws that were used to hold that in place. And now just screw these back in. Okay, let's take a little look and see how they're aligned. There we go. There we go. We've got our first one in. Let's screw that in a little bit. Let's grab our next screw. Let's get that in the opposite corner. So that will help align the other ones. Yep. Okay. Let's get the last guy in. Okay, let's give this a good twist down so that we're nice and locked in. Okay, so now what we can do is actually mount this guy back on there in place. And what I'm going to have to do is, as we do that, I'm going to have to get these guys and get these things into here and then screw them down. So let me go do that, and then we can get set up to actually test and see what the amplifier says. Okay, so here we go. I have what we have set up, and this is the front end check that it asks to do, is to set the incoming signal generator to be minus 30 dBm, and that's about a 20 millivolt peak-to-peak signal. And then what it's asking to do is we will connect the output of that amplifier, which is actually W8, and that's this line here. This normally goes back into A16 at the back, and what I've got is I've got that connected into my oscilloscope here. And so if we go and look at the oscilloscope, you can see that, oh, let me just drop it down a bit so you can see that. You could, let me get that back in so you can see that. You can see that basically the peak-to-peak signal that we're getting is about 19.2 millivolts. With all these cables, that's sort of to be expected. You know, if I take that off there and drop this on here, you know, we're 19.8. So we're losing about 0.6 of a millivolt throughout this, or 0.4 of a millivolt throughout this whole system. So this should still be able to tell us whether or not we're getting the gain, because remember, what we want to see out of here is an increase of about 24 dB. So what we're going to do here now is actually go in and I'm going to see if I can get this close to 20 millivolt, and then we'll go through the special function to turn on the amplifier and see what we get on the output there. Okay, so here we have about 20 millivolt. You know, it's varying a little bit, you know, coming in. And so now what I want to do is I want to turn on a special function, and that special function is special 1.7. And what that's going to do is that's going to turn on the amplifier and add 24 dB of gain. So at that point, what I should see is a signal here somewhere between 0.285 and 0.35. So let's go in and point 1.7 special, and there's our amp in. So let's turn down our gain a bit, and there you see I'm seeing about 300 millivolt, which is in between. Let me go and actually set minus 30 dBm again, and you know, we're seeing 288 millivolt there, which is, you know, 290, which is the low end of the amplifier, but it's still within range. So I'm not sure if that amplifier is actually bad, or if it's just very close to the minimum gain there. So what I'm going to go do now is just have a quick look to see what the procedure is to do frequency drift, because I was failing to do frequency drift when I tested it before, and let's see whether I can do the frequency drift this time. Okay, so now we're going to try and set up for that frequency drift measurement. So I'm in 50 megahertz here, and I've got it turned off automatic track mode. It's just reading the signal. So what I'm going to go do is set ourselves into tuned RF level, and then I'm going to set my signal generator for minus 33 dBm, and then enter 4.2 special, which turns on the IF synchronous detector with a measurement average time of 1 second, and then 50.6 special, which is going to show the voltage that I'm reading on that synchronous detector. And then I'm just going to step my amplitude up until I get 3 volts here. Let me come back. Yep, close enough to 3 volts there. So, now that I've got 3 volts, I'm going to press clear, and then I'm going to just do a set reference level. And so we're close enough there. So now, what I want to do is set my step attenuator to 10 dBm, then enter 4.2 special, then 9.2 special, and set the reference again. Okay. Now I'm going to move my frequency up and down by 10 kilohertz, and I'm going to do it until I see an error 1. Now I should be tracking this value to see if I'm actually inside the frequency drift, but what I was getting before when I would go do this is I would get error 19. And error 19 is signal too low. Well, now I've got error 1 there, so I'm going to go back the other direction. So let's go back to 50 megahertz. So now I'm going to go back down now and see what I get, and see if I get an error 1 going the other way, or if I get an error 19. I got an error 1 there, but I probably can keep going a bit. Nope. So I'm getting error 1, which means that I've drifted too far out for the signal to track, and that is sort of 49.995. It's about a 10 kilohertz range, which is what the error is supposed to give me. I think we may have been able to solve that issue by reflowing the meter, the connectors on the amplifier. If that's the case, then that was an $8,000 fix to keep this in specification. So I think that's interesting, and we might go do a full run through at some point and see if it passes calibration. Alright, hope you found this interesting. Catch you later. Bye.